Hello. Operation amplifiers. What they are, what you can do with them, and some general design tips. So, you've probably heard of me maybe use them. But there's a lot of bits of information you may not know that can help if you're trying to design something or trying to get something working that uses a different type of op-amp to what you have. Now, to go back to the beginning, operational amplifiers were invented many decades ago. I think probably the very first ones were probably based on vacuum tubes, valves. And the essence of those, typically, whether it's a vacuum tube or a bipolar transistor type, is a long tail pair, which you've almost certainly seen at some time. Two transistors with the emitters connected, or the cathodes connecting valves, with a load resistor. So as one turns on, the other one is turned off as by the shared voltage. Anyway, to get onto integrated ones, the earliest ones, you use a 15 volt supply, a positive and negative 15 volt supply, so 30 volts total. That's very common. They don't have to work on that, but that's a very, very common voltage, because the output cannot pull all the way to either supply rail. And a common standard in a lot of equipment is a 10 volt signal swing. The output's got to be able to go between plus 10 volts and negative 10 volts. And to guarantee it can do that and drive some level of loading for the next stage and its own feedback circuit and things, it needs some kind of overhead, some excess supply voltage to allow for the voltage drops in the output circuit of the amplifier. I mean, a 741, if you ever looked at anything to do with op-amps, you've probably heard of a 741. That's kind of the Model T version of an op-amp. It's one of the very early ones. It's about the first one that didn't need extra components to stabilise it, and you could use it just in isolation, if you like, with resistors and whatever for feedback. The earliest ones were actually in TO5 transistor cans. That's an example of a board from 1979. And you can see these are the 741s on it. And that's quite an interesting circuit, actually. That it's a good design example, which I'll post a link to as well. Now, the basic op-amp, the original ones before integrated circuits were built with transistors, and they only had an inverting input. They didn't have a non-inverting input like the integrated ones and all later devices do. So they were always configured as an inverting circuit. And even now, a lot of circuits that use op-amps have the positive input tied to either 0 volts if it's a dual supply, or the mid-supply bias point if it's a single supply. I mean, that's a typical single supply setup. At some point in the circuit, for a single supply, there'll be a resistive divider with some kind of decoupling capacitor on it to generate a midpoint voltage. So just as with the positive and negative 15 using the 0 volts as the reference, this uses half the supply as reference, except the supply is unipolar rather than bipolar. So if it was working on positive 12, as I've shown in the example here, that would be about 6 volts. And that gives, again, the maximum practical signal swing, positive and negative, of the reference voltage. Now, some circuits might not need that. Some circuits might only need a single supply and work from near 0 volts. And some types of op-amps can include 0 volts in their input range and near to 0 volts in the output range. I mean, the LM324 is one of the standard examples of that that's been about for many, many years. It can't pull all the way to the positive rail. On a 5 volt supply, you'd be lucky to get more than about 3.5 to 4 volts, or at least guaranteed through any op-amp. But it can go down very near to 0 volts, so it's got a reasonable swing. Now, regardless of the supply, an op-amp, you can think of it as having near infinite gain, or at least ludicrously high gain. You cannot use it without feedback because the slightest variation in input and the output will just switch between as high positive as go and as far negative it will go, and not do much useful. It must have a feedback circuit around it to be stable and work. And an op-amp in itself, a conventional one, is actually comparing the negative input to the positive input, or 0 volts if you're using a grounded input. The positive terminal is the reference voltage, if you like. The negative terminal is being continuously compared to that, and it's the difference between the two that define what the output does. In a very common type of circuit, an inverting amplifier like this, the output has a resistor to the negative input, and the signal input also has a resistor to the negative input. If you put a voltage on that input, say on that circuit put a 1 volt positive on the input, that amplifier will try to do everything it can to hold the voltage difference between inputs at 0 or very close to it. So to do that, it has to take the output to -1 volt, so the midpoint of that resistor divider is at the same as the input. Now, I'm talking relative to that reference point, whether it's single or dual supply. It's not actually necessarily 0 volts if it's a bipolar circuit, or sorry, a unipolar circuit like this, but relative to the reference voltage, it will balance, because I've got two equal resistors. The voltage at the output will be equal but opposite to the input, to try and hold that potential divider at the midpoint the same as the voltage on the non-inverting pin. If you change the ratio of those resistors, say that was 100k, 10 times the size of this, then the circuit gain would be 100. For 100 millivolts at the input, you get 1 volt at the output, but the opposite polarity. Again, it's trying to hold the two together. And I can demonstrate that on here. Now that is an actual vintage 741. I have a scope connected to, I want to bring this scale up. I want to bring this way up. I have a scope connected to the input point, which is feeding a 10k resistor there, and that's that red, which is the first channel, and on the scope itself that's a yellow signal, that's the yellow trace, and the output, which is there, is connected to there, and that's the input 10k resistor, that's the output 10k resistor. I've tried to lay the wires down so you can see which pins they connect to. I mean, although this is a vintage 741, it's the only 741 of type I've got, I've arranged the pins the same as the dual in-line type. So this is pin 1, that's pin 8, pin 4, pin 5, and the pin numbers then match exactly a dual in-line version, an 8-pin dual in-line type. So the inverting input's on pin 2, non-inverting is on pin 3, negative power on pin 4, pin 5 is not connected, output on pin 6, and positive power on pin 7, which is as I drew it on this sheet. So that's matching the pinouts. Now I've got a pot here, 10k pot connected across the power, and if I turn that, that's the yellow trace. So as I'm turning it positive, the purple, which is the output, is going to, subject to the errors in the scope and the bit of noise it picks up between levels, is going to the same voltage but opposite, until you get to a certain point. I mean, the yellow trace will go up to nearly 15 volts as the scope set to, 5 volts of division, so each dot in the vertical lines is 1 volt. You can see it runs out of steam trying to go that far negative. Beyond that point, I'm still varying the input, but it's almost 2 volts less than the 15 volt supply. If I go negative on the input, and that's trying to go positive, and that's about 1 volt less. It's a little bit better, but there's still that bit of range where it stops varying on the output because it just cannot pull the output that close to the supply. So that's an inverting amplifier with unity gain, the same voltage in and out, but opposite polarity. So regardless of the supply, that's the basic configuration I'm using, and same value input and output, so its ratio of output to input is 1, so the voltage ratio is 1, same input and output. If I change that feedback resistor to 10k, then that will have a gain of 10. And that's going to go, so that's a point. That's now trying to go with infinite gain, so if I try and take it through near 0, it'll just flick across. I mean, the gain's probably in the region of 10,000, 100,000. I'm not quite sure on that, but probably in that type of range for a bipolar op amp. So trying to get it stable is next thing to impossible without feedback. So I'll put that in there. So that should then control the gain. Now the output is varying 10 times higher because the resistor is 10 times higher than the negative one, the negative feedback. So that's now still got that 10k, and that one is now 100k. So it takes 10 times the voltage on the output relative to the reference point to match the voltage on the input, but the opposite polarity. So you can see that'll now limit at quite a low level on the input because the output just can't swing anymore, so it can't follow it. Now another option, another use, which you can combine lots of different things. You can have gain and other functions in the same thing. Switch back to that 10k, so I've got gain of 1. Another thing you can do with a simple inverting op amp is have more than one input. I find the right page. So you can add extra inputs to it, just to the summing point. Now, oh, by the way, that point that tries to hold at 0 is called a virtual earth, because relative to the op amp reference on pin 3, that will stay pretty much the same voltage no matter what you do with the actual inputs to the overall circuit and whatever the output does. As long as it's within its voltage range on everything, there'll be pretty much 0 voltage difference between those two pins. Anyway, off track again. So you could add one extra input, 2, 3, 4, and you can have different values of resistors to give different relative gains through the circuit. Now, I've only got one other pot connector set up here, so I can only use 2 inputs. But if I add an extra 10k again, for simplicity, between that pot there and that, and then bring in the other scope channel, bring in channel 2 and set that to 0 about. Now just find the 0 on the inputs. So yellow's channel 1, I want at 0. That's input 1. Blue's channel 2, which I also want about 0. Oh, hang on, I've set that to the wrong place. It'll be there. That's better. That's why I'm getting silly readings. Right. Okay. So everything at 0 output. Now, if I set, say, 3 volts about on input 1, the input 2 still at 0. I can't see those. If I set 3 volts at input 1, input 2 still at 0. That should be the other way around, shouldn't I? Got the no, not mess. So input 1, which confusing is yellow, and I've got yellow and blue, and the yellow and blue there. I didn't realise that before I started. 3 volts there, 0 volts there, and I'm getting, subject to the scope tolerance, I'm getting -3 out, so it's inverting an equal signal. Now, if I then put, say, 4 volts on that one, so about there, now it's been, I'm finding no point, no noise now, then I've got 7 volts, or near enough so, on the output. It adds the 2, it's a summing amplifier. Now, depending on the input resistors, you can scale the inputs to different readings, and the feedback resistor can be used to change the overall gain. But this has been used classically, or this type of circuit has been used classically for analog computing, literally for numeric calculations, scientific calculations, and early simulations before digital computers. Now, analog computers were a very big thing in the 60s and 70s. The other thing this is if you had coupling capacitors, it's an audio mixer. Because mixing in audio sense is actually linear addition of signals, or the voltage of signals, which is exactly what this is doing. So you add +4 and -4, you get 0. So that is the basis of a mixer, and you can have as many inputs as you want. You could have a level control on each one, either as the input resistor or potential divider on the feeding the input pot, and you have a multi-channel mixer, as long as you use a suitable op-amp. Now that's the next bit. That's some of the circuits. Oh no, sorry, there's one other thing first, before we get into frequencies and things, and that is a differential amplifier. Now, it'd take too long to really reconfigure this, and I don't have anything suitable set up for it. But this is one of the most useful circuits you probably don't know exists, or maybe don't know exists, if you don't use op-amps much, and that is a differential amplifier. You can see I've redrawn and rearranged the resistors slightly on the feedback side and the output, so everything's in line through on either side. What that does is it takes the difference between the two input voltages, it inverts it because it's still, that side still got the inverting feedback configuration, but whatever voltage you get between those two, as long as the inputs and the output voltage remain in the working ranges for whatever op-amp and voltage supply you're using, that will duplicate the input difference voltage between the output and the VREF point. Now you could have the VREF point as ground, in which case the output would be the difference between the inputs inverted, but either side of ground depending on the polarity of the inputs. Or say you're using it for a microprocessor reading voltage. If you make the VREF say 2.5 volts if you're using a 5 volt microprocessor analog to digital converter, and the output drives the ADC input, then you will read the difference between those two up to 2.5 volts of either polarity, even if these are on a totally different voltage. Say you're reading across a current sensing resistor and a power supply, as long as everything is set up correctly voltage range wise and the gains and everything, you could read, say, the difference between 2 points that's grounded at one end and a series resistor current shunt resistor in the output of a power supply at that side, or vice versa for the polarity, and you'd completely convert or shift it to work with a reference at 2.5 volts and that either side of it. Or you could have the reference at 0 volts and a single polarity input with that output going 0 to 5 volts. So even if one of these was, say, going between 10 volts and 15 volts, so 10 volts supply and going between 10 and 15 on the other one, or something like that, you'd have to use the resistor ratios correctly. Now, I made notes on these. I'll put a link to this document. The input resistors need to be exactly equal, so you really need to be high tolerance resistors or use a slightly lower value on one of them and a preset resistor so you can tweak it to get the values exactly equal. The output resistors need to be equal. Then the gain is the ratio, as before, of the output resistors to the input resistors. So that would have a gain of 1, a unity gain. And you can have high gain, or you can have have it higher than 1. Say that you could use 100k for those two, and it give you 10 times gain on the output compared to the input. Or you can have it the other way around. You could use it if you're working on a high voltage system. Say you're using something that a microprocessor on 3.3 volts or 5 volts, but you trying to measure something that's in say a 12 volt or 24 volt power supply. If you scale the voltage down, you can offset it. Say you had those at 100k, you'd reduce the voltage by a factor of 10, the input voltage by a factor of 10, but you could have quite a lot higher voltage, because if that was grounded, that's at 24 volts, you only got about 2.5 volts on that within your working range. And that one will try and stay the same as always with the op-amp. The negative input will try and match the positive as long as everything's within range. So you can measure a difference in voltage outside the supply range of the microprocessor. Now you might then, depending how big the difference is, you might then need to add an extra op-amp to boost it back up again. But you can have a simple, say times 10 gain or whatever you want after this, to get back to whatever scaling you need. And that's one of the slightly less common but very useful options for using the things on configuration. Now, if I don't lose track of what I'm doing again, op-amp selection. That's what can trip you up very easily if you're not familiar with the different types, if you don't know the ratings off by heart. As I say, the 741's a classic, and you see a lot of stuff using that. But as I say, it's basically in op-amp terms, it's the Model T Ford. It works, but it's not very good specifications in comparison to a lot of the new stuff. It's a very basic bipolar op-amp with limited output facilities and limited frequency response. It's noisy compared to all the new stuff. It's not really good for audio or anything like that. Now, the things to look for when you're looking through an op-amp datasheet, as well as the supply voltage range, let me find the right bits in this one. The common mode range. Oh no, sorry. Well, first level, I'll finally go through in sequence. Input bias current. That is how much current the input pins may draw. And this 741, that's a maximum of 500 nanoamps, half a microamp, which might not sound like a lot, and it isn't. But if you think about it, the effect on a resistor, say on that 10k circuit I was showing, the Thevenin equivalent of the input, the two 10k resistors, is 5k. So half a microamp on 1k would have half a millivolt. It's about 2.5 millivolts offset that could be caused by that, which isn't a lot. And in an AC application, audio, well, not audio, but on one of these at least, it wouldn't matter. But if you're trying to do DC offset or DC measurements, let's say feeding something like an op-amp, then it can cause erroneous readings. So actually that's something I meant to mention earlier. The way around that on a bipolar amp or something that takes significant input current is whatever the impedance of the input there is, the negative the inverting input. If you've only got the two 10k resistors, it'd be 5k. This has got 4 of them, so it's 2.5k. You'd put a similar value resistor in series with the positive input to whatever reference or ground connection it's using. So that also has a similar voltage drop due to its input current, and that cancels out most of the error. Some 8-pin op-amps have the facility for an offset null, which is an external potentiometer, which you can see in the data applications in part, which you can use, which adds an adjustable bias, positive and negative of the open circuit, if you like, on unbiased voltages, so you can trim out minor errors like that as well. Anyway, back to this. Input voltage range. Again, that's the guaranteed working range of the inputs on a 15 volt supply on a 741 is only plus or minus 12 volts. The last 3 volts near the supply may be lost. It may not respond properly. And if you think of that, if you're trying to use a 741 on a 5 volt supply, if it doesn't work within 2 or 3 volts of either rail, then basically it doesn't work. So if you ever see someone try to use a 741 on a 5 volt supply, you'd be very lucky if it works at all or does anything sensible. Now, here we go. The voltage gain. Now this is giving you an idea of how much the output changes for a change in between the inputs. Typically, minimum anything from 20 to 50 volts per millivolt, so 20,000 to 50,000 minimum. And a typical example gives a gain of 200 volts per millivolt of input difference. So it's you can see why it jumps about if you try and do anything with it without a feedback resistor to control it and stabilize it. And again, the output is only guaranteed to go to within 3 volts of the positive and negative rail when operating on 15 volts. And in fact, if it's got a significant load, 2k load rather than 10k load, it might not even go nearer than 5 volts to it. So you need a full 15 volt supply just to get a 10 volt signal out. So that's something you've got to be very careful of. And even a lot of the newer op-amps that are very useful and commonly used, like a TL074, which is a brilliant op-amp for audio and things like that. It's very low noise. That doesn't pull the output to close to either supply. It's not suitable for single rail operation near 0 volts. If you want it to work in a 0 volt bias state, then with dual supplies, well, then you've got to have dual supplies and with a good headroom on them, the same as with this. Maybe not quite so much. I don't know if I'll get to that in a minute, hopefully. But again, this the old 741, that's can operate plus or minus 15 volts, or in some version of it could even operate to plus or minus 20 volts, which is somewhat unusual. It's not so common. Anyway, other types. Now, this is the 324, which is one I mentioned. It's, again, a very common one. There's also, technically, probably no, there isn't a 322 on this. It's an ION 393, I think, is the dual version, which has the same specs, but it's only an 8-pin with 2 amplifiers in it. So, input bias current, the 324, 45 to 100 nanoamps instead of up to 500 nanoamps, as with the 741. So it's a fifth the input offsets, input loading than the 741. Common mode range goes from 0 volts, which is the negative supply because it can operate at a single supply, to within 1.5 volts of positive rather than 3 volts. The output swing when I can find it. And what's the gain? Yeah, 100 volts, millivolt, typical 100,000. Somewhere there should be an output. Oh, it's given the other way around. It's given the output current at different voltages. So the 15 volt supply, the output 2 volts from ground. It can supply a minimum of 20 milliamps. So the sink current, which is if it's pulling down towards negative rather than pulling up towards positive, so at 12 milliamps it's only guaranteed to be within 200 millivolts of ground. It can't actually guarantee to pull the output to ground with a load feeding from positive. The best way to use one of these single supply op-amps is have a load resistor to ground to take a little bit of current from the output circuit when the output is trying to pull towards 0 volts to kind of help the op-amp, rather than having a load connected to power that's trying to hold the output away from 0 volts. And that'll give you a better response. So that, for a single supply op-amp, that's not bad. It will work down to 5 volts, but the signal swing then is only about 3 volts. But it can be used at 5 volts. Again, you can use it with a dual supply. The maximum is quite a bit higher, I believe. So you could use it 505. That's a common application for microprocessor stuff. You've got a 5 volt supply. You can use a negative 5 volt as well to give you both voltages, so you can work to near 0 volts accurately. That's a TLC274, which is a CMOS one. I thought I included that because that gives the full schematic of the op-amp internals, which some datasheets do, some don't. Depends on the manufacturer and the age. Older datasheets were a lot better at giving the internal circuits. But you can see that's got the FET equivalent of a long-tailed pair. In fact, it's got 2 of them. That's a current bias circuit there, and that's the actual. It's inverted P channel rather than N channel. Those are the sources, the inputs to the gates, and the drains feeding the load circuit, and one of those goes to the output. It's as you turn it that way up, it's a commoner long-tail pair configuration. That FET replaces a load resistor because it's a little easier to fabricate than resistors in ICs. Okay, I'll not bother reading through all that. Now, this is a rather nice one. They're not as cheap as some of the others, but this is a CMOS rail-to-rail input and output. Now, this is the type that you can use on very low voltages and still get near enough full supply span on the input and the output. It's also got stupidly crazy low input bias current. I can't remember what offhand, but I said about loading the inputs. Those were in the orders of nanoamps. Depending what version you get, it can be, worst case, 4 picoamps input current. It's astronomically small. Common mode voltage goes from 0.3 volt below the negative supply to 0.3 volt above the positive supply. So the input common mode with the working range for the inputs is actually slightly larger than the supply voltage. It's got a similar gain to the others. On sourcing output, it's not symmetrical. That's one of the slightly odd things with it. So it's 120,000 on sourcing, only 35,000 on syncing. So it's not quite symmetrical, but as long as it's used sensibly, that doesn't matter. The gains are still so phenomenally high that if you're doing anything reasonable with it, it'll work fine. So somewhere on here, what's the output swing? Now this assumes that it's using that biasing circuit I showed, or similar functionally. I've lost my page. That one. That's for using it as a full range op amp. It's assuming that it's working around half supply voltage. If you look at this, it's everything is referenced to V plus over 2, in other words half supply. It also gives it several voltages, but the 2K load, which is a fairly low load for an op amp, fairly low value resistor should I say, you can get on a 5 volt supply, it can run to somewhere between 4.7 4.9 volts or 0.1 volts, so within 0.1 of a volt of the supplies on a 5 volt supply. It can't quite force the outputs to 0 or 5 volts if the load is to the centre of the supply. If you're using it for something like an ADC, you didn't quite need the full range, then, as I mentioned before, putting a load resistor to ground instead of 0 volts would help it pull down, and you get better accuracy near 0 volt range. It will work up to 15 volts single supply, so you can use it on 12 volts or plus or minus 5 volts. And it's generally a nice versatile amp, but it's not particularly high frequency response. Now that is the other parameter you need to look at. Somewhere in each datasheet there will be either a slew rate or a gain bandwidth. This has both, and that allows you to calculate what its frequency limits are for any given gain. So the gain bandwidth product, that is gain times frequency. So if you're using it with a gain of 1, theoretically it'd be able to track a signal at up to 1.5 megahertz. If you're using it with a gain of 100, then it'd only be able to track a signal up to 15 kilohertz. And ideally you want to stay well below that to minimise errors, because it's pushing the limits. Now, have I got a 274 in this or not? Yes, I have. TL074, sorry. Right, oh, that's one that also gives the input circuit. TL074, TL072. Again, that's using the long tail pair, but that's a hybrid. It's using FETs for the input devices for the high impedance, but a transistor as a current source, and bipolar again transistors for the loads. Now the specs on the TL074, these actually TL074, TL084 are actually, oh that's an 08, sorry, that's the 08 as well, I've got mixed up. But they are actually, actually print it double-sided. 074 and 084, or TL072, TL082, are actually the same dies in production, the same devices. But then during testing they're selected to be one or the other. The ones that have got the lowest noise for audio applications and lowest distortion overall are classed as 07 devices, and then the 08s are ones that have better parameters in other ways. So the TL074 or TL072, it's got quite a range of offset current. It can be 5 to 100 picoamps. The Kollmorgen input range on a 15 volt supply could only be plus or minus 11 volts. So it's even less than some of the others, even less than a 741. The output voltage again is not phenomenal. It's not like some of the others. You've got 12 volts on 15 volt supply, or even down to 10 volts positive and negative with a lower load resistor. Compare that to the 08 version. The 08 version's got slightly, well, depending which version you get, which suffix, it could be the same, it could be slightly higher input current. Oh, in fact, it's generally quite a bit higher input bias current. Common mode range is about the same. Peak and output voltage is about the same. I was thinking the bias current, I thought the bias current actually was a bit better on these. Input bias current of 65 to 200. Peak, oh, sorry, I'm getting mixed up between offset and bias. 65 to 200. Yeah, the typical input bias current is half that of the 07. So they tend to be a little bit lower input loading for applications where input loading is critical. Somewhere in there I thought they gave a load as well. Anyway, slug rate, the unity gain, which is again you can use that to calculate the frequency response for a given signal level. That's 13, minimum of 8 to 13 volts per unit microsecond. Now what's the figure on that one? If you even got that far. There we go. No, I lost it. Oh well. Anyway, yeah. So if you want best audio response, use a TL07 series. If you want best computing or DC accuracy, use a TL08 series. But they're pretty much interchangeable for most things. Noise isn't critical. Anyway, I think that's getting on for it. I've probably forgotten something I was going to say. A fuse for a project to work at the moment. Oh well. Yeah, to go back to this just quickly, as I said, I will post a link to this. It is a part of a copyright system. It's copyright by Inland Motor, or Kollmorgen. I'll post a link to the original file on their site. Because if you're interested in analog design or servo drives or anything, it's worth a look. And that is that actual board. And as I was mentioning, this has the series resistors on the positive inputs of the amps. So they've got two 10k resistors, just as I had before, so it's around 5k Thevenin impedance, and they've got a 5k series resistor to match it. Oh, that's another application I meant to mention. If you replace the feedback resistor with a capacitor, you get an integrator. The output will ramp steadily depending on the time constant of the side of the capacitor and the input current through the resistor. The output will ramp one way or the other at a speed proportional to the voltage you put on the input point, the input resistor, which can be very useful in something. You can use it for analog timing and or error correction, if you like, to cancel out drifting circuits, which is what this does. This is part of the current control circuit on it for the servo drive, and that's will progressively ramp to cancel out the error, because the error is being compared back through other parts of the circuit, to optimize the current into the motor for the speed needed. And to reset it or disable it, you take that as a FET connector across it. They're using that as a simple analog switch, which just shorts out the capacitor. And you can actually see that as Q1 on the board there. That shorts out the. I would think that big capacitor there, 0.33 C1. Now that's C2. C1. That's C1 down there. That's the integrator capacitor. And that's what sets the time constant in proportion to the voltage at the input. So you can use it if you connected that to a square wave input. You get a sawtooth output as long as it was fast enough to stop it clipping, again to the full voltage limits. But yeah, it's an interesting little design example. It's kind of does everything right, based on principles that were used back then. I mean, this is dated 1979 on the ICs and 741s. I don't know if you can quite see that date code, 7918 by the look of it. 7918, so 18th week of 1979. When this was originally drawn, 71, 72. This date's from. So it's literally 50 years old. This schematic. This is one of the later ones. There happened to be an incredibly good drive for the time, and still compared to a lot of analog drives now. Anyway, I'm rambling. I hope that this is of interest. I will post links to the relevant bits and a link to the file with my drawings in it. And please let me know if you have any comments, thoughts, suggestions, and please hit like and subscribe. Okay, thanks for watching. To make it easier, if you want to copy this circuit and also to prove that this antique has the same function and pinout as a newer type, I'll put newer, I don't know what I've got, just a random, slightly newer Opamp in there, a dual line plastic one. It's an LF351, which I think will work on 15 volts. I hope it will. So I'll drop that in instead. Let me just disconnect the power. In the same position. Zoom in a bit on that now. You can see the circuitry connections, as I said originally. It's inverting input pin 2, non-inverting input pin 3, which has 5k to 0 volts in this configuration. Negative power is pin 4, output is pin 6, and positive power is pin 7. And let's say this thing, which if I can get it to focus, that's the date code or manufacturer code. That is an LM741H. TO5 cam. It's actually the one of the types on the front of that datasheet I showed earlier. Okay, that's all connected up, and that should now, if we put power back on, that'll help. That should work exactly the same. So I've got the inverting summing function. So anything I was doing with different configurations and that you can do with any typical dual inline op amp that's rated for the voltage you're using. I mean, it's an oddball can. Got to use those for repairing those other boards I showed, because they have a kind of circular pinout for the PCB pattern, and these fit easily because that's what they're made for, but you cannot get one of the dual inline op amps to fit without doing crazy things with the pins, and you'd be very lucky for it to actually go in at all. So yeah, that's why I keep these, which can in some places be stupid prices now. But anyway, okay, so that's it, working with a standard plastic dual inline IC. a single op-amp type, because the vast majority use the same pinout regardless of the exact type. So the differences of voltage restrictions and input and output voltage ranges. But for general single op-amp, then that's the commonest pinout. Okay, that's it. Right. Thanks for watching. Any comments, questions, please let me know below, and please hit the like button. It makes lots of difference to the way that my stuff's presented on YouTube. Okay, thanks. Bye.